It should be there. If they drew it right, this should have been twice what the height of this one. It doesn't look like quite twice. Oh, this way? No, I don't think so. It looks that way because it's relative to its amplitude. It is, right? You know, but it's I think it stays in phase. At least it should have, unless I drag the auto shape, right? Okay. So yeah. Anyway, constructive, destructive, right? So here is the rule. If the distance from the sources is, if you have two sources creating the same sound, let's say, right? If it's an integer number of wavelengths, you get constructive interference, right? So this is the difference in wavelengths for B, is that it's the same. The integer is 0, right? Notice that crest is meeting crest, trough is meeting trough, crest, crest, trough, trough, right? Okay. If I move it out, if I move B an exact wavelength closer to us, yeah, what happens? Well, it's the same thing, right? Crest meets crest, trough meets trough, yeah? Yeah, yeah? Okay, crest meets crest, trough meets trough. Right? I've got another demonstration that I realize I didn't set up, but I'll, right? And then another, this is now 2 wavelengths, right? It's now 2 wavelengths away. Again, crest is meeting crest, trough is meeting trough, like this, right? Okay? So that's the rule. If it's constructive interference, it's 0 wavelengths difference. If you have 2 sources, right? 1 wavelength, 2 wavelengths, 3 wavelengths. In general, the difference is n lambda, right? Where n is 0, 1, 2, 3, right? And then the rule for destructive interference is that you have a half wavelength difference, right? So there it is. We are half a wavelength closer. We move A, B half a wavelength. How do I know it's half? Well, because the crest here is meeting the trough of that one, right? Trough here meets crest, right? So that'd be quiet. And again, this is now, this is half a wavelength. What's this one? 1.5 wavelength, isn't it? It's not 1 wavelength, it's 1.5, right? This one is 2.5, right? So destructive interference, you have to say n plus 1/2 times lambda, where n is 0, 1, 2, 3, etc., right? N is, what is that? Is that an integer? We call that integer. Is 0 positive or negative? It's both. At the same time. Ha! Ha! I don't know. Yeah? That's our rule. And I'll show you how to solve these things. Okay, but first we have some demonstrations. Okay? So if we have a 2-source pattern, so let's say we have 2 speakers in a room, one, and they're both putting out the same, let's say they're putting out the same frequency. And I know these are the same frequency because the wavelength is all about the same, right? Okay. What happens is that creates in the room, and this is like we're looking at it like waves on the surface of the pond, but it creates places where, and here what they've labeled here is where the crest is meeting the crest, right? So the crest from this guy, right, is meeting the crest from this guy right there, right? Those are going to add up and make a super crest. How about the spot right in the middle there? What is that? That's not crest meets crest. What is that? Trough meets trough. Trough, this trough here from this guy, right, is meeting this trough. There, in between these lines is a trough, right, from this guy. So this is going to be a super hole in the water. This is going to be a super wave on the water. And then halfway in between, this is a crest meeting a trough. Here's a trough from this guy, right? And here is a crest from this guy. This is destructive interference there. So that's why they're labeling all these midpoints like that. That's destructive interference. This is constructive. And there's also constructive interference there and there in the middle of all these things, right? There and there, right? Constructive there, there. Destructive here, there, there, there. They're just labeling some of them, right? Okay. Now, wouldn't it be cool if we could hear this? Yeah. Oh, I think that would be cool, right? Okay. So I've got a couple demonstrations for you. Okay. The first one is one of the most annoying ones, right? But I'm going to turn off those things. I'm going to turn the volume down so our ears don't quite bleed. And this is a very cool program. It's got like a 30-day free trial, but I actually bought this thing. It's like, ooh, okay. Sine wave, 782. How about we make, let's make it 343 hertz. Okay, same as left. Okay, sine wave. Oh, there we go. at 343 meters per second, okay, our wavelength, the speed of sound, v is f lambda, right? The speed of sound is 343 meters per second, and that's 343 hertz, right? That's at 20 Celsius and, you know, some atmospheric pressure, right? Okay, what's our wavelength then? The lambda is 1 meter, right? Okay, so what I want you to do is I want you to get up and I want you to plug one ear and I want you to walk around the room and see if there's places, come on, promenade. See if there's places that are quiet and softer. Do you hear that? Yeah, there definitely are places where it's loud, places where it's soft. I wonder if the microphone's picking it up. It's kind of cool, isn't it? Try doing a little plie. Bend at the knees. Is it a vertical? Yeah, it changes. If it didn't change, just go to a different place. Right? Yeah, that's kind of wild, isn't it? Is it driving you crazy? Yeah, it kind of is, isn't it? Oops, sorry. Yeah.
I have one of those on my phone. They're so entertaining.
The mosquito tones?
Yeah.
Yeah. All right.
They're so entertaining.
What's a cosine wave?
A cosine wave is.
Will it sound different?
Oh yeah, you can make a cosine. I don't know if it's got just a sine, because obviously what you could do if you want cosine is you can do phase shift, right? So let's go on. Right, you can shift it, and I think this is degrees. Let's try 90 degrees. Oh, we'll hit. It changed, didn't it? Isn't that wild? Right. So it's actually putting out the phase shift. We shifted at 90 degrees, 180 degrees. I'm going to find a loud spot. Right. Let's make this 180. That made it different, didn't it? Yeah. Yeah, so we're shifting it basically, and then I'm going to do this with. I know it's like this 12 in high school parking lot after school. I can also do this with a laser. Yeah. Well, okay. Here's the problem with getting perfect cancellation here in the physics room, right? Is that what you need to do that is you would have to have the speakers. You have to have the walls be anechoic, because at any given point in this room, you're not only hearing the sound from the speakers, but the sound from any reflections, and who knows what phase that's in, right? So you need an anechoic room. Then you need to have a spot where the sound intensity, because the thing that's going on in this PowerPoint that's not at all clear, okay, is that they show these things, but isn't this crest smaller than that crest? Yeah, the farther away you are, the energy is spread out over a greater area, right? So in this case, it's dropping off 1 over r because it's 2 pi r. It's a circumference, right? But in a sphere, it's 4 pi r squared is the area of the sphere, so it's dropping off with r squared. So you actually have to be the same distance from each source, or the far source would have to be louder, right? So those noise cancellation earphones they're closer, but they're not quite as loud, right? Because big paper machines putting off just tons of noise hatred, right? Okay, so let's get the laser first shining on the screen, and then these speakers. In order to get interference, you've got to have like a pattern like that sits still. You've got to have the sources play the same note, right? So this laser, all of that light it's monochromatic, Okay, so everything in this laser